All right, let's look now at the interaction of that groundwater with the surface water. To begin with, let's look back at the water table. Here is the water table, and the precipitation is hitting the surface. It's infiltrating and then percolating down through these sediments to the water table and then entering the saturated zone. That water is flowing down slope or down gradient of the water table and hits the edge of this slope here, comes out in the seepage face, which is basically a spring, and enters into that stream down below. So that's what's happening. I wanted to go back to that image and show you the water seeping out of that cliff. And that is what we're seeing in the image here, that the water table has intersected with the cliff. Okay, yeah, that's showing that slope with the water coming out of it and entering into a pool of water down below. Okay. Groundwater interacts with the coastline. So in this image, on the left side is the ocean, and on the right side is the sandy shoreline. The water on the shore face here is actually groundwater that is seeping out of the sandy shore face. There are other ways that groundwater interacts with the surface water. The top left is showing a limestone cave system. The water is finding ways to trickle through those caverns and come out on that cliff face. The image to the upper right is an unconformity. An unconformity is a break in the sedimentation record or the geologic record. And that image down below, that's a crystalline rock like a granite. It has very little permeability or porosity. And then above that are sedimentary rocks. The water has infiltrated through the sedimentary rocks, has hit that granite, and is now traveling sideways along that surface. Oh my. Ooh-wee. For the bottom left corner, that is water that is moving along a fault zone. Faults, when they move, crush up rocks, creating their own porosity and permeability. So the water has found that pathway to the surface. The bottom right here is a fault, and the rocks on the left side are permeable and have some porosity to them. The water is going down the gradient on those rocks, hitting that fault surface and riding up along that interface where the rocks on the right are crystalline and don't have that porosity to them. Caves. Caves are a place where really the surface and the groundwater really interact. On the left is a cave in Italy, and the river, a tributary, flows through the cave and hits that daylights and hits that other stream. The bottom right, we have stalactites holding on tight to the ceiling, and stalagmites growing as they might grow up to the ceiling. When they come together, growing, then they form what's called a column. Those are examples of speleothems, cave formations. Here are some fractures along a road cut here in the Blue Ridge Mountains, southern Appalachian Mountains. What you have is water seeping along foliation plains and bedding plains. When that water hits the surface, it usually just looks like wet rocks. But in the winter, it looks like frozen waterfalls. In the desert, we have what we call oases. Oases, mini oasis. Those form when the underlying geology, you have rocks that have been folded, and the rock that outcrops at the surface is an aquifer, and some of that water spills out onto the desert floor, and the aquiclude below it holds that water like a little bowl, and that's an oasis. These are hot springs in Yellowstone National Park. Later, you can click this link and see a little story from the national park about the geysers. Hot water is going to dissolve ions, and when the water comes to the Earth's surface, the pressure changes and there's a precipitation of those ions. In this case, it's a calcite called travertine. Okay, here are lakes. Lakes and groundwater interact, where the water table intersects the surface, lake can form, and the water table then is the surface of the lake. So here is a upstream lake that is actually recharging the groundwater. This groundwater is flowing and entering into this little pocket, making a lake, and then down gradient again, maybe a stream here in the valley. That's pretty common. Up on this flat area, this terrace of the river is a little wetland. So that's a pretty common configuration to have the water table kind of come and go between these surface water bodies. So there are different setups for lakes. So real simple diagrams here. A seepage lake would be a lake where the groundwater flows into the lake. You don't see a surface expression of it so much, and then it flows just out the other side. Or you can have a lake where the groundwater flows into the lake, and then there is a discharge out of a channel. So this darker blue is a channel coming out of the lake. So here is a lake off of Howards Creek Road. This is Potato Hill Lake, and groundwater flows into it, and then it becomes Howards Creek that flows down Howards Creek Road. So this would be an example of the second one here, the groundwater dominated lake. Another kind of lake, here we have both kind of dominating it, the surface water and the groundwater. These tributaries enter the lake and groundwater is flowing out of it. On the right, there's groundwater and surface water flowing in and out. So a lot going on in both of those situations. Examples here. Here is Pashaw Lake in Maine, and a tributary flows into the lake. Some groundwater is flowing through the lake, and then there's a distributary flowing out of the lake. And they're all going to feed the Penobscot River down there near the coast of Maine. All right, reservoirs. We've made a man-made anthropogenic water bodies. This reservoir is filling up a valley. Maybe it's flooded these two V-shaped valleys of two rivers, and then the reservoir has a flat side to it. That's the dam. And the water is allowed to come through that dam either to generate hydroelectricity, or maybe it's a flood control reservoir. So that is another kind of lake. Who knew there were so many kinds of lakes? On the right is a terminal lake where all the water that is flowing in that watershed hits the lake, and then the only way water gets out of that lake is through evaporation. Here is Claytor Lake in Virginia, kind of near-ish to Roanoke. It's dammed here. It's a reservoir. The reservoir, though, the bedrock geology allows for seepage outside of that reservoir. The light colors here are groundwater, but there is, when the dam releases, it allows for the new river to flow. And here's Mono Lake in California. If you ever have a chance, you should visit Mono Lake. It's on the edge of the Rocky Mountains in the basin there in California. Really fantastic place, cool rocks. Mono Lake was part of, it's a terminal lake, let me just say that, so water flows in but doesn't flow out. It was part of the LA aqueduct system. They were stealing water from Mono Lake, interbasin transfer is what it's called. We're taking it over to LA, but the water levels were dropping too much. You can maybe see on here old, like the bathtub ring where the water was higher. It was exposing sediments, which was not good when those get entrained by the wind. But also, these islands in the middle of the lake are important habitat for different shorebirds and migratory waterfowl. And as the water levels were dropping, predators were able to get to the islands and eat eggs or baby birds, and that was a no-go. So that community of Mono Lake ended up suing LA, and now they've had to go through restoration efforts to get it going again. Okay, I've thrown out these terms before, a gaining stream and a losing stream. That's in reference to the groundwater. So if a stream is a gaining stream, it's gaining water from the groundwater. A losing stream loses water to the groundwater. So I would say east of the Mississippi, most of our rivers are gaining streams. They get water from the groundwater. It's what keeps them flowing when we don't have rain. Whereas west of the Mississippi, there are rivers that are ephemeral. They maybe only flow in the spring or only flow when there's rain or snowmelt. Most of those then are called losing streams, where the stream is losing water to the groundwater. All right, here's just a thought question. What controls the flow rate of groundwater? The rate of groundwater flow. Number 1, the gradient of the water table. Letter B, the permeability of the rock. C, how fractured the rocks are. Or D, all of these. D, right? It's D. All of these. Caves. What makes caves? I'm going to turn my face off. Get me out of the way here. The formation of caves is through the chemical weathering process called dissolution. The rocks are dissolving. The kind of rocks that dissolve are the carbonates, those rocks that have the chemical formula of the mineral calcite, CaCO3. Dolostone has some magnesium in there as well, but CaCO3 or Mg, parentheses, Mg, comma, Ca, parentheses, CO2. Okay, those rocks dissolve in even slightly acidic water and form cave systems. So at the top, here's a solid block of limestone. It gets water down into some cracks. Those cracks over time are going to grow into big caves and crevices. A sinkhole can form. Here's one that formed in 1981. We get them in Florida, where the bedrock is a lot of limestone. Buoyancy, there's groundwater holding up the rocks. Maybe there's a cave down below. There's water in it, though. And say we pump out and discharge this water down below, the roof collapses and causes sinkholes. So that's one of the ways that sinkholes form. Caves around the United States, but not Alaska and Hawaii or Puerto Rico. The stripy ones are evaporite rocks. So these are caves in rock types salt and gypsum. The rocks that are in pink are karst. Karst is the description of the topography created by caves from evaporite rocks. And then the orange pale peach, that is karst from carbonate rocks. So we are in Boone, which is right here at the tip of my arrow. And it's just a hop, skip, and a jump to eastern Tennessee or southwest Virginia, where there's lots of caverns to explore. There are, or they used to be in the before time, maybe in the after time, there will be cave trips to Worley's Cave through outdoor programs. I highly recommend. All right, so here is the coast. This is the Atlantic Ocean. Here's some barrier islands. And this is Florida, and these rounded, I'm going to move the cursor around, those rounded lakes and ponds and that area, those are where sinkholes formed and then were flooded with water. So underneath those springs, those there's going to be a big cave system. The topography, we call that, again, is called karst topography. Here are some formations of caves. So a look at what the hill slopes, the interior of the hill slope will look like if there were caves. I already mentioned sinkholes. There's a direct surface water, cave water, groundwater interaction. This is all limestone. We have debris, soil, and rocks kind of caving in, falling in on that cave there. The groundwater table is going to be at some level within the cavern system. Streams can disappear and appear just out of the ground. Yep. Here's some more Italian caves, just really pretty caves. Again, the stalagmites on the floor, stalactites on the ceiling, they come together to form columns. In Vietnam, there on the left, that's amazing karst topography. And on the right, the tower karst of China. These are two places that are, I guess we'll say, internationally protected, important places in the world. And they form from the carbonates weathering and forming those spires and just a beautiful landscape. In Ireland, the shoreline is a karst shoreline, and this is what the bedrock looks like. You walk over it, but easily like fall down a couple feet down into these crevices near the beach. The Dominican Republic has a karst shoreline, and then here in the United States, we have Mammoth Cave National Park in Kentucky, beautiful cave system. These are travertine deposits like Yellowstone National Park. At Yellowstone, they're hot and protected and owned by the American people. Here in Turkey, they're privately owned, and you basically rent it by the hour as a tourist, and you can get into these travertine cups and spend your afternoon holiday there in Turkey. Travertine, remember, is the name of that calcite formation. More about speleothems, stalactites, stalagmites. I talked about those. Flow stones are just this ripply flow here. The draperies are these stalactites that have kind of like grown together in a drape. They can look like ribbons or bacon. And tiny ones back here, those are called straws. All right, we study groundwater. There are different ways to study it. We can look at it directly by just what's the topography of the land, what's the geology, what's the bedrock geology. We can drill down. So if you're drilling a well to put it in a drinking water supply or pump some water out, a drilling company will come and drill down, and they will investigate groundwater flow, what is the porosity and the permeability of the bedrock, and the chemistry of the water. All those different things can come out of drilling for putting in a well at your house or your business. Indirectly, we can do geophysical surveys. So standing back, not touching it, but using fancy equipment, whether it's satellite imagery or imagery to image the subsurface, those kind of ways. We can then take that information and model what the subsurface looks like instead of directly knowing. So here is what a driller platform looks like. When these are going down the highway, they tilt the tower backwards, but put it vertical to drill down into the land, and then the geologist or soil scientist looks at a book and looks at the color of the sediment coming out and classifies it. We also have people that study river discharge. This person's name is Joey Anderson. He was a hydrologist. He turned into an accountant. But he did a senior thesis at ASU studying the discharge of Boone Creek. Here is the chair of the Department of Geological and Environmental Sciences, Bill Anderson. He is doing geophysics. He's sending waves down into the subsurface. They're bouncing off surfaces, and they're coming back to his tablet, and he's able to model and look at the subsurface that way. He gets things like this: peat layers overlain by a gravelly beach, and the different layers that he sees and the depth to those layers based on the travel time of those waves. And then he takes that information, he comes up with a model. So as a geologist, he uses lots of computers. So computer science is a big part of geology these days by modeling that subsurface and the subsurface flow. You can have somebody else collect this data for you. You take that data and you put it in the computer and come up with those models. And then you can make a map. So here's a map of the water table. So here is like a road map with maybe some farms on it. And then each of these data points is telling us the depth to the water table. So over here on a Kiwia Road, it's 150 meters down to the groundwater, and down here off Albion Lane it's only 110. So the water's flowing from up high off Aisquia Road down through Rupert Road and down to Albion Lane. So on the map over here, we can contour that and draw these arrows showing the groundwater flow.